Quite science journeys. Saturn is one of the most familiar shapes in the solar system. A pale golden sphere wrapped in thin bright rings suspended quietly against the dark. It looks calm, balanced, and almost light. That appearance has helped create one of the most repeated ideas about the planet. You may have heard it before. Saturn is so light people say that it would float in water. The idea spreads easily because it feels playful. It turns a distant world into something you can picture. A giant planet gently resting on an endless ocean, rings and all. What makes the statement interesting is that it is not completely wrong. If you take all of Saturn's mass and spread it evenly across its enormous volume, the average density comes out lower than liquid water. That number is real, measured, and well established, but that same number is also where the confusion begins. Density does not describe strength or solidity. It does not describe how tightly matter is bound. It only describes how mass is averaged across space. Saturn is not light in any physical sense that matters. It contains about 95 times the mass of Earth. Its gravity is strong enough to shape matter on a planetary scale layer by layer over billions of years. Nothing inside Saturn is loosely arranged. Nothing is gently stacked. The mistake happens when density is treated as a physical description rather than a mathematical shortcut. Density is simply mass divided by volume. By design, it compresses everything inside an object into a single value. That average hides structure, it hides pressure, and it hides how matter changes when gravity has had a very long time to press inward. The floating idea quietly replaces Saturn with a simplified image. Low density becomes lightness, lightness becomes weakness, and weakness becomes emptiness. None of those steps follow from the original measurement. Saturn's low average density comes from its composition. The planet is made mostly of hydrogen and helium elements, lighter than the rocks and metals that dominate Earth. Spread across an enormous volume, that composition lowers the average, but lowering an average does not remove mass. Saturn contains far more material than any rocky planet. It is simply distributed under conditions that have no everyday parallel. Another problem with the floating idea is scale. Floating is something small objects do inside a larger environment. Saturn is not small, and it does not exist inside anything that could support it. Saturn has its own gravity. If it were placed near a vast body of water, Saturn would reshape the water rather than rest on it. The comparison breaks the moment gravity is allowed into the picture. Pressure is the other missing piece. On Earth, pressure increases slowly with depth. Inside Saturn, pressure rises rapidly. As you move inward, layer after layer of material stacks above you. Hydrogen atoms are forced closer together. What begins as gas thickens, flows, and gradually stops behaving like gas at all. There are no empty chambers beneath Saturn's clouds. There is no hollow interior waiting below the surface. There is only matter compressed by gravity acting across an entire planet. This is why the floating idea points in the wrong direction. It encourages us to imagine Saturn as weak when it is powerfully bound. It suggests lightness when the real story is about compression. Density in this context is not a measure of fragility. It is the outcome of composition and pressure combined. Change either one and the number changes. To understand Saturn, intuition needs to be reset. Familiar comparisons have to be separated from physical reality. Instead of stopping at averages, the story has to follow gravity inward. In this journey, we will move through 3 stages. First, we will look carefully at why the floating idea exists and what it actually describes. Next, we will examine what density really measures and what it leaves out. Finally, we will travel inside Saturn itself, where pressure reshapes matter into unfamiliar forms. Saturn may float in a thought experiment, but that experiment leaves out almost everything that makes Saturn what it is. The real story is not about floating. It is about how matter behaves when gravity has had billions of years to press it into place. Seen this way, Saturn becomes less of a clever comparison and more of a lesson. A reminder that planets are not defined by shortcuts. They are shaped by forces that work slowly, deeply, and without regard for human intuition. Understanding begins when comparisons give way to mechanisms grounded in physics. That is where this story truly begins. To understand why this idea exists, it helps to define density in the most practical way possible. density is not a hidden property. It is simply a description of how much mass is packed into a given amount of space. If you take 1 kilogram of water and 1 kilogram of rock, the mass is the same. The difference is space. The rock occupies less volume, which is why it feels heavier when you lift it. It is heavier per unit of space. Water has a density close to 1 by definition. Many rocks are 2 or 3 times denser than water. Air is far less dense, which is why it feels light and offers little resistance. In daily life, floating is really about averages. A log floats even though some parts of the wood are dense. A sealed bottle floats even when the plastic itself is heavier than water, because air inside lowers the average density of the whole object. A boat can float with metal parts, cargo, and people. What matters is not the density of each piece, but the average density of the entire shape, including the space inside it. Floating does not ask how something is built in detail. It asks how the total mass compares to the total volume. This is the exact move the Saturn meme makes. It treats the entire planet as one object with one average number. Layers do not matter, pressure does not matter, only the ratio survives. When scientists calculate Saturn's average density, they combine its mass and its size. If you imagine spreading that mass evenly across that enormous volume, the result is slightly less than liquid water. That calculation is correct. In that narrow sense, the floating statement is true. But it is important to notice what is actually being compared. Not Saturn as a physical place, but a mathematical average. A single number standing in for an entire planet. Averages are useful, but they are also dangerous when taken too far. They flatten structure, they hide variation, and they encourage simple images where complexity belongs. 2 objects with the same average density can have completely different interiors. A hollow shell and a solid sphere can share the same number. A layered object with a dense center and a light outer region can share it too. The average alone does not tell you which case applies. This is where the floating idea begins to drift away from reality. Low average density becomes a feeling of lightness. Lightness becomes a feeling of weakness. Weakness becomes a guess of emptiness. None of those steps follow from the measurement itself. Saturn's low average density comes mainly from what it is made of. Hydrogen and helium dominate the planet. These elements are lighter than the rocks and metals that shape Earth. Spread those light elements across a vast volume and the average density drops. But lowering an average does not remove material. Saturn still contains an enormous amount of mass, more than any rocky planet by a wide margin. Another quiet assumption hides inside the floating idea. On Earth, floating happens when an object interacts with a larger environment. A log floats in a lake. A ship floats in an ocean. Saturn does not exist inside a larger container. It has its own gravity. It defines its own environment. If Saturn were placed near an enormous body of water, it would not behave like a passive object. Its gravity would pull the water inward. The water would rise, flow, and reshape itself around the planet. The familiar image of support breaks down completely. This shows why floating is a metaphor, not a description. It highlights a numerical relationship, but it does not describe a real situation. It simplifies the planet into a scene that cannot physically exist. Pressure is the other missing ingredient. On Earth, we meet gases at low pressure. They feel thin, they spread easily, and they give way when pushed. Inside Saturn, pressure rises quickly with depth. Hydrogen that behaves like a gas near the top does not stay that way. It thickens, flows, and gradually stops acting like gas at all. The floating idea ignores this transformation. It freezes Saturn at the level of a number, never follows gravity inward. The planet becomes a surface image rather than a layered system. This is why it helps to treat the meme carefully. It is not false, but it is incomplete. It points to a real calculation, but it does not explain what that calculation means. Floating in this context is a comparison, not a conclusion. It tells you how Saturn's average density relates to water. It tells you nothing about how Saturn holds itself together. Once that boundary is clear, the idea loses its power to mislead. It stops implying fragility, it stops suggesting emptiness, and it stops standing in for physics. The number can stay, the image has to go. Saturn can have a low average density, and still be massive, strongly bound and deeply compressed. Those statements do not contradict each other. They describe different aspects of the same planet. The floating idea survives because it is easy to remember. But understanding Saturn requires moving past what is easy and toward what is accurate. To do that, the next step is to look more closely at density itself, not as a label, but as a tool. A tool that works well in some situations and fails quietly in others. Density feels decisive. It looks like the kind of number that should settle an argument. If something is dense, it feels solid. If something is not dense, it feels weak. That shortcut works often enough in daily life that it becomes instinct. But density is not a measure of strength. It does not measure rigidity. And it does not describe how matter behaves when it is pushed, squeezed, or held together by gravity. Density is an average, and averages hide structure. It tells you how much matter is averaged into a given space and nothing more. This limitation becomes clearer when we look at familiar contradictions. A steel ship floats. A small stone sinks. The steel is far denser than water, yet the ship stays above the surface. The reason is not strength or weakness. It is geometry. The ship contains a great deal of empty space. Air fills the hull, lowering the average density of the entire structure. The steel remains dense, but the ship as a whole does not. Now reverse the situation. A piece of foam can sink if water fills its pores. The material itself has not changed. Only the balance between mass and volume has shifted. In both cases, density explains the outcome without saying anything about how strong the material is. Steel does not become weaker when it floats. Foam does not become stronger when it sinks. This is the first correction intuition needs. Density does not describe resilience. It does not describe how matter responds under stress. It only describes how mass is distributed. For small objects, this limitation is easy to miss. A rock is mostly rock. A block of wood is mostly wood. Internal variation is small enough that the average feels representative. For planets, that is no longer true. A planet is not one material. It is a layered system shaped by gravity. Each layer exists under different pressure and temperature conditions. When we quote a planet's average density, all of that complexity collapses into one number. The difference between surface and interior disappears. The role of compression vanishes, and the fact that matter changes behavior under extreme pressure is hidden. Gravity is the reason this matters. Gravity pulls inward, and the deeper you go, the more mass presses down from above. On Earth, this effect is present but limited. Pressure increases with depth, but materials remain in familiar states. Rock stays rock. Metal stays metal. On giant planets, gravity changes the rules. As mass increases, gravity becomes strong enough to compress matter far beyond its ordinary state. Atoms are forced closer together. Electron behavior shifts. The same material begins to act differently. This means density reflects two things at once. It reflects what the planet is made of, and it reflects how strongly that material is compressed. Two planets can share the same average density for completely different reasons. One might be made of heavier elements but compressed less. Another might be made of lighter elements but compressed much more. The number alone does not tell you which story applies. This is why density should be treated as a clue, not a verdict. It points toward deeper structure without describing it. Confusion grows when density is mixed with everyday language. Words like light and heavy carry emotional meaning. They suggest effort, resistance, and fragility. Density does not carry any of that meaning. It does not know how something feels. It only tracks ratios. This is where the Saturn misunderstanding takes root. When people hear that Saturn is less dense than water, they imagine gas behaving like gas does on Earth. Thin, easily displaced, barely held together. But gas is only light when gravity is weak. Under strong gravity, gas becomes dense, heavy, and tightly bound. The word gas describes composition, not behavior. Behavior depends on pressure. Under enough pressure, the difference between gas and liquid fades. Under more pressure, entirely new states appear. Average density does not capture those transitions. Another hidden assumption sits inside the idea of volume. We tend to imagine volume as empty space waiting to be filled. For planets, volume is shaped by gravity itself. A planet does not choose its size freely. Its radius emerges from a balance between gravity pulling inward and internal pressure pushing outward. Change one and the size changes. This means a larger planet is not necessarily emptier. It may simply be resisting compression more effectively, or it may still be retaining heat that keeps it expanded. Saturn's low average density reflects this balance. Its composition temperature and gravity all play roles. Remove any one of those factors and the number would change. Density is useful. It helps us compare planets. It helps us see broad patterns across the solar system. But it does not explain those patterns. If density truly measured strength, Earth would be stronger than Jupiter. If it measured solidity, small metal objects would outperform giant planets. Those conclusions make no sense. Strength in planets comes from gravity. Structure comes from pressure. And behavior comes from physics acting under extreme conditions. Density is the visible shadow of those deeper processes. Quiet Science Journeys makes long, calm episodes that slow complex science down without losing precision. Subscribing helps you find the next one, and it supports the work behind the series. Once this distinction is clear, the floating idea loses authority. It becomes a numerical curiosity rather than an explanation. Interesting, but incomplete. To understand Saturn, we have to move beyond averages. We have to follow gravity inward. We have to watch how matter responds as pressure increases. Density sets the stage, compression writes the story. And that story only begins when we stop asking what a planet might float in and start asking how it holds itself together under its own weight. Saturn can be held in the mind as an image again. Rings drawn like a thin, bright line, a planet turning slowly beneath them. The surface stays quiet from far away even when the interior is doing constant work. A world where the same material changes by pressure alone, layer after layer, without a single hard boundary. From here, the next step is not a new fact, it is a new direction. Downward into the place where averages stop being helpful and the layers become clearer. Saturn does not feel heavy when we look at it. Its colours are pale, its edges are soft, and its rings make the planet seem balanced rather than burdened. From far away it is easy to imagine Saturn as light, but Saturn holds roughly 95 Earth masses. That mass is gathered into a single world held together by gravity that never stops pulling inward. Inside Saturn, the story is not about airiness, it is about compression. To understand the compression, imagine moving downward in slow steps. At first, you're still in the region we call atmosphere, where clouds and hazes carry the visible patterns of the planet. Hydrogen and helium are still a gas here, stirred by winds and warmed by sunlight. Descend a little farther and the change is gradual, not dramatic. Pressure rises because more material stacks above you, and collisions between molecules become constant. The gas thickens, heat is trapped more efficiently, and motion begins to feel less like weather and more like flow. This is where Saturn starts to resemble an ocean. Not an ocean of water, but an ocean of hydrogen becoming denser with depth, a continuous medium rather than a thin sky. The material still moves, but it does not give way the way air does on Earth. As you continue, inward pressure climbs far beyond anything found at Earth's surface. Hydrogen enters a liquid state, and the boundary between gas and liquid becomes less meaningful than the fact that the material is now a dense fluid. Helium remains mixed through much of this region, though its behavior depends on temperature and pressure in ways that can vary from layer to layer. The deeper you go, the more gravity dominates the environment. Every layer presses down on the one below, and the planet's interior responds by becoming harder to compress. The fluid becomes more tightly packed, and the same elements begin to act unfamiliar. At high enough pressure, hydrogen does something remarkable. Atoms are pushed so close together that electrons begin to move freely through the fluid. The material becomes electrically conductive, a state known as metallic hydrogen. Despite the name, metallic hydrogen is not a solid slab like iron. It is best imagined as a dense conducting fluid shaped by extreme pressure and high temperature. This layer likely occupies a large fraction of Saturn's interior, and it changes what the planet can do. A conducting fluid inside a rotating planet can generate a magnetic field. Saturn rotates quickly, and motion in its deep conducting layers drives electric currents. Those currents produce Saturn's magnetic field, which extends far into space and shapes the environment around the planet. Notice what is missing from this journey. There are no empty chambers beneath the clouds and no hollow spaces waiting below a thin shell. Each step inward reveals more matter under more pressure held in place by gravity. Near the centre, Saturn is expected to contain a region enriched in heavier elements. Rocky and icy compounds, along with other heavy materials, likely contribute to a central core or core-like zone. The exact shape of that region is uncertain, because at these pressures, boundaries can blur and mixing can occur. Some models suggest that heavy material is partially dissolved into the surrounding layers. Instead of a sharp, solid sphere, the centre may transition gradually into the fluid above it. Even with uncertainty, the implication is consistent. Saturn is not hollow, and its mass is not concentrated only at the surface. Saturn's low average density remains true, but it is a consequence of composition and structure together. Hydrogen and helium are light elements, and even when compressed, they are lighter per atom than silicates and metals. Spread across Saturn's vast radius, that composition lowers the average while the interior remains strongly bound. There is also another ingredient shaping Saturn from within: internal heat. Saturn still releases more energy than it receives from the Sun, meaning heat is leaking upward from deep layers. That heat helps drive convection, slow circulation, that carries energy outward and keeps the atmosphere active above. In certain pressure and temperature ranges, helium may become less willing to remain mixed with hydrogen. If that happens, helium can form droplets that fall inward through the surrounding fluid. As the droplets descend, gravitational energy is converted into heat, adding to Saturn's internal energy budget. This effect is sometimes described as helium rain, not because it looks like rain in the usual sense, but because it is a settling process inside a deep fluid world. The details are still being refined, but the general idea fits. The larger theme composition and pressure can reorganize matter in ways that affect a planet's evolution. Rotation shapes the interior as well. Saturn spins quickly, and rotation influences how flows align, how convection organizes, and how the planet's shape bulges at the equator. Winds at the cloud tops are the visible part of a deeper moving system, though exactly how deep those winds extend remains an active question. What we can measure directly is Saturn's gravity field. As spacecraft pass by, their paths shift slightly, and those shifts reveal how mass is distributed through the planet. The measurements do not paint a picture of emptiness. They paint a picture of a massive layered body with motion and structure beneath the clouds. So when the floating idea suggests lightness, it is pointing at the wrong feature. Saturn's surface appearance is gentle, but its interior is defined by weight and pressure. A planet can look soft in sunlight and still be an engine of compression inside. If you want one clean image to carry forward, let it be this. Saturn is a deep ocean of matter with no hard floor, growing denser with depth as gravity presses inward. At the top it behaves like weather, lower down it behaves like fluid, deeper. Still it becomes conductive, and near the centre it holds heavy material mixed into a core-like region. Nothing in this structure is delicate. Saturn is not held together by a thin shell, but by gravity acting on an enormous mass. The softness is only what light shows you, and the reality is what pressure does. One more subtle change happens: as you descend, the meaning of distance itself shifts. Near the top, a few kilometers can separate one cloud deck from another, and weather patterns can change quickly. Deeper down the scale becomes tens of thousands of kilometers, and conditions change slowly in space but relentlessly in pressure. This is why Saturn has no simple surface to point to. There is no single boundary where you can say now you have arrived at the planet. Instead, you cross thresholds of behavior where the same material becomes harder to compress, where flow becomes heavier, and where heat moves in broad, slow currents. Those slow currents matter for what we see. The bright bands and dark lanes in the atmosphere are not painted on a shell. They are part of a moving system that is fed from below, shaped by rotation, and limited by how easily heat can rise through dense fluid. So the interior story is not a separate topic from the view through a telescope. The soft glow and the clean geometry are surface clues. They hint at a world made of light elements, but they sit on top of a deep, compressed interior that does not match the first impression. Even in silence, it is heavy. With that interior in mind, the phrase gas giant starts to sound different. Gas describes the ingredients we see near the top, but it does not describe how those ingredients behave at depth. To keep the story accurate, the next step is to separate the word gas from the idea of emptiness. We use simple labels to keep distant worlds manageable. But inside Saturn, the label is not the behavior. To move forward, we will keep the composition and update the intuition. Gas is a word that feels effortless on Earth. It can mean thin air in a room, steam rising from a kettle, or the hiss from a valve. Gas suggests space between molecules, easy motion, and a kind of lightness. That is why the phrase gas giant creates an instant picture. A giant planet made of gas sounds like a giant thing made of almost nothing. It suggests a swollen sphere, mostly empty with a little material spread out loosely. Saturn does not match that picture. The word gas in gas giant describes composition, not structure. It tells you which elements dominate, not how those elements behave, when gravity compresses them for planetary distances. On Earth, gas is usually low density because pressure is low. Molecules are far apart, they move freely, and they fill whatever space is available. When pressure increases, gas changes. It becomes denser, it pushes back, and it begins to behave less like a diffuse cloud and more like a fluid. In Saturn, pressure does not increase a little. It increases steadily and then relentlessly, because more and more material lies above any depth you choose. The same hydrogen that looks like air near the cloud tops becomes thicker as you go down because gravity will not let it stay expanded. This is the first correction the label hides. Gas does not mean empty, it only means the dominant ingredients are elements that are gases under many ordinary conditions. Behavior depends on pressure and temperature, not on the everyday meaning of the word. A useful way to keep this straight is to separate chemistry from texture. Chemistry tells you what the atoms are. Texture tells you how those atoms act together in their environment. Inside a giant planet, the texture changes continuously, even when the chemistry stays mostly the same. On Earth, we're used to sharp boundaries, air above water, below rock beneath that. Those boundaries exist because the ranges of pressure and temperature are narrow, and because gravity is modest. In Saturn, the ranges are vast, and gravity is strong, so the boundaries blur. Gas turns into dense fluid without a clean dividing line, and the planet becomes a continuum. This is one reason the label gas giant misleads. It makes the planet sound like a giant atmosphere. In reality, the visible atmosphere is only a thin outer region where light escapes. Most of Saturn is deeper material under higher pressure, even though it is made of light elements. If you want an image that fits the physics, imagine Saturn as a layered ocean of matter. Near the top, the ocean behaves like weather with clouds, winds, and turbulence. Deeper down, it behaves like a heavy fluid that carries heat and responds to rotation. The point is not the exact depth of each layer. The point is that the planet is filled with material all the way down. The second correction the label hides is the role of gravity as a sculptor. Gravity holds the planet together and it squeezes the planet inward. The squeezing is not a side effect, it is the organizing principle of the interior. As mass piles up, pressure rises and matter is forced into denser arrangements. This is why size is not a measure of emptiness. A planet can be large because it is warm, because it is young, or because its gravity compresses it less than a heavier planet. Heat creates pressure that resists compression. Gravity creates pressure by adding weight above. The radius is where those influences balance over time. This balance also explains why the phrase gas giant can sound like a contradiction. Gas is associated with expansion, but giant planets are held together by strong gravity. What looks like expansion is actually the equilibrium size for light elements under heat and compression. The planet is not puffed up by nothing. It is supported by pressure inside real material. Everyday intuition about gas also fails when we think about weight. Gas on Earth feels weightless because it is sparse, but gas still has mass. A column of air above your head has weight, and that weight creates atmospheric pressure. We live inside that pressure, so it feels normal. Now scale the idea up. In Saturn, the column above a deep layer is not a few kilometers of air, it is tens of thousands of kilometers of hydrogen and helium. The weight of that column produces pressures that change how matter behaves. Under those conditions, the word gas stops describing texture in any useful way. It remains meaningful only as a statement about composition. This is where the phrase gas giant should be handled carefully. It is a category, not an explanation. It helps separate Saturn from rocky planets, because Saturn is dominated by hydrogen and helium rather than silicates and iron. But it does not tell you whether the inside is thin, thick solid, or fluid. For that you need pressure physics. There is another misunderstanding built into the label. On Earth, gas often means something you can move through easily. Air yields to a wave of the hand. A scent spreads through a room. This trains the mind to imagine gas as weakly held. In Saturn, deep material is not weakly held. The planet is bound by gravity and the interior is under pressure. Even if the ingredients are hydrogen and helium, the result can be a dense fluid with significant inertia. The material can flow, but it is not a near vacuum, and it is not a gentle mist. This difference matters when people picture Saturn as a balloon. A balloon is light because the gas inside is low pressure compared to the air outside. The balloon is held together by a thin skin. Saturn has no thin skin holding it together. Saturn is held together by gravity acting on its own mass. We can check the picture using measurements that do not depend on words. Spacecraft paths shift as they pass Saturn because Saturn's gravity pulls on them. Those shifts reveal a massive body, not an airy shell. They also show that the planet is not uniform because gravity varies with latitude in ways influenced by internal structure and winds. Saturn also emits heat. It releases more energy than it receives from the Sun. This tells us there is internal energy moving outward through the planet slowly and steadily. The term is a label for ingredients, and ingredients can become surprising states when pressure rewrites their behavior completely. The label gas giant is still useful as long as it is paired with the right intuition. It should trigger the thought of light elements under gravity, not the thought of emptiness. It should suggest a deep fluid world, not a balloon. If you hold that corrected intuition, other familiar phrases become clearer too. Atmosphere becomes a thin, visible region, not the whole planet. Surface becomes a word for where light escapes, not a solid boundary. Depth becomes a change in pressure and behavior, not a descent toward empty space. This corrected intuition also prepares the comparison with Jupiter. Jupiter is called a gas giant as well, yet its stronger gravity compresses similar ingredients more intensely. The difference is not that one is real and the other is airy. The difference is how mass, heat and time set the balance between size and compression. So the phrase gas giant is a starting point. It tells you what Saturn is mostly made of. To know what Saturn is like, you have to add the missing ingredient gravity acting over depth. Once gravity is in the picture, gas does not mean empty. It means that the simplest elements can build a massive world, and under pressure, those elements can behave in ways that feel nothing like gas on Earth. Saturn remains calm in appearance, but its interior is a continuous response to weight. With that in place, we can return to a more familiar comparison: Saturn and Jupiter side by side. Their shared ingredients make the contrast clean, and their different masses show how compression changes everything. Hold the word gas lightly for a moment. Keep the chemistry and let the texture change with depth. Picture Saturn as a long gradient, not a shell, not a balloon, not a hollow sphere. A quiet ocean of material growing denser as gravity gathers it inward. Let that picture stay quiet for a moment, a planet without a surface, only depth. Then bring Jupiter into view beside it, another giant world shaped by the same gravity. Saturn often feels softer when it's compared to Jupiter. Both planets are large, both are wrapped in clouds, and both are made mostly of hydrogen and helium. Yet Saturn spreads out more with a larger radius relative to its mass, and that difference invites an easy mistake. It is tempting to think that puffier means weaker. If Saturn is less compact than Jupiter, then its interior must be less substantial. That conclusion feels natural when we rely on everyday experience with materials. On planetary scales, that intuition fails. To understand why Saturn is puffier than Jupiter, it helps to compare the two planets in physical terms rather than visual ones. They share similar ingredients, but they do not share the same mass. And mass changes how gravity shapes everything else. Jupiter contains more than 3 times as much mass as Saturn. That difference is not subtle. It means Jupiter's gravity is significantly stronger especially in the deep interior where compression matters most. Stronger gravity produces stronger compression. Inside Jupiter, material is squeezed harder and deeper than inside Saturn. Hydrogen is forced into denser states across a larger fraction of the planet, and the interior becomes more compact as a result. Saturn follows the same physics, but it does not push the material as far. Its gravity is still immense, but it is weaker than Jupiter's. The same ingredients respond by remaining more expanded. This is what puffier actually means. It does not mean loosely held or fragile. It means that the balance between gravity pulling inward and pressure pushing outward settles at a larger size. A planet's radius is not set by mass alone. It is set by how that mass responds to pressure and heat. Gravity tries to compress the planet. Internal pressure resists that compression. Saturn sits at a different point in this balance than Jupiter. One reason is formation history. Jupiter formed quickly and accumulated mass efficiently while the solar system was young. Its gravity grew strong early, and compression began while the planet still held a great deal of heat. Saturn formed more slowly and gathered less total mass. With weaker gravity, it never compressed its interior to the same degree. That difference established early still shapes the planet today. Heat plays a central role in this story. Internal heat creates pressure, and pressure resists compression. A warmer interior stays expanded longer. Saturn still releases more energy than it receives from the Sun. That excess heat comes from slow contraction and from processes deep inside the planet. As long as heat is present, it helps support a larger radius. Jupiter also releases internal heat, but its stronger gravity overwhelms that support more effectively. The same amount of heat has less influence on size when gravity is stronger. As a result, Jupiter becomes more compact for its mass. There is also a compositional difference in how heavy material is distributed. Both planets contain elements heavier than hydrogen and helium mixed into their interiors. Those heavy elements increase density and affect how the planet responds to compression. Jupiter likely contains a larger fraction of heavy material overall, or a distribution that concentrates mass more strongly toward the center. That configuration enhances compression and contributes to its smaller radius relative to mass. Saturn contains heavy material as well, but it may be spread more gradually through the interior. Instead of a sharply defined dense center, some of that material may be mixed upward into surrounding layers. The result is a planet that remains more expanded. These details are still studied, but the direction of the effect is clear. Mass distribution matters not just mass itself. Rotation adds another subtle influence. Both Jupiter and Saturn rotate quickly, which causes their equators to bulge outward. This rotational support slightly counteracts gravity, making the planets wider than they are tall. The effect exists in both planets, but its impact depends on internal structure and on how deeply winds and flows extend. In Saturn, the combination of rotation and internal layering contributes to its overall shape. We learn about these interiors by watching how the planets pull on passing spacecraft. As a spacecraft flies by tiny changes in its path, reveal how mass is distributed inside the planet. In Jupiter, the signal points to a more strongly compressed interior. In Saturn, it points to a structure that remains more expanded. These are not impressions based on images. They are measurements based on gravity, and gravity reflects mass and compression directly. Another important principle emerges from this comparison. Mass and radius do not scale in a simple way for giant planets. Adding mass does not always make a planet larger. Beyond a certain point, adding mass increases gravity faster than it increases size. The additional gravity squeezes the material more tightly, and the radius can stay nearly the same or even shrink slightly. Jupiter sits closer to this regime. Despite its much greater mass, it is not dramatically larger than Saturn. Gravity is efficient at packing material as mass increases. Saturn with less mass has not crossed as deeply into that compressive regime. Its interior remains more expanded and its radius reflects that difference. This distinction matters because size alone can mislead. In everyday life, larger objects often feel lighter when they are less dense. On planetary scales, larger can simply mean less compressed. Saturn's lower average density compared to Jupiter does not come from emptiness. It comes from lighter elements combined with weaker compression and sustained internal heat. Change any one of those factors and the planet would change. If Saturn had more mass, gravity would compress it further. Its radius would shrink and its average density would rise. If Jupiter had less mass, it would expand. With similar ingredients, it would appear puffier, even though nothing essential about the material had changed. The physics would be the same, only the balance point would shift. This lesson extends beyond our solar system. Many exoplanets appear larger than expected for their mass, and are often described as puffy. In most cases, that puffiness reflects heat youth or strong energy input from their stars, not hollowness. They can be strongly bound worlds with expanded outer layers held together by gravity while remaining large in size. Back at home, Saturn's puffiness also connects to time. Giant planets cool slowly. As they cool, they contract. Saturn has been shrinking gradually for billions of years as it loses internal heat. In the distant past, it was likely larger than it is today. Jupiter has also contracted, but it began from a more massive and more compressed state. The planets we see now are snapshots in long histories of cooling and compression. Their sizes record how gravity, heat, and composition have interacted over deep time. There is no weakness in this process. Saturn's gravity remains strong enough to maintain deep pressure gradients. Its interior still reaches conditions where hydrogen becomes metallic and electrically conductive. Its magnetic field is generated by the same physical mechanisms as Jupiter's. The difference is one of degree, not of kind. So when Saturn looks puffier than Jupiter, the correct interpretation is not that Saturn is less real. The correct interpretation is that Saturn is less compressed, warmer, relative to its mass, and shaped by a slightly different evolutionary path. Puffier does not mean weaker, it means differently balanced. Once that correction is in place, Saturn and Jupiter stop looking like opposites. They become 2 points along the same physical spectrum. Similar ingredients, different mass, different compression, different size. Those differences teach a simple principle. Gravity is the sculptor of giant planets. Composition provides the material. Heat and time decide how tightly that material is packed. Saturn's size is not a flaw or an exception. It is a record of how a planet responds when gravity is strong but not overwhelming. With that comparison in mind, we can return to the original floating idea and ask what it really gets wrong, and why it continues to feel convincing, even after the physics is clear. The Saturn floats idea survives because it feels like a clean fact. It takes a complicated planet and compresses it into a single image, a giant world resting on an ocean. That image is memorable, and it is easy to repeat. In one narrow sense, the claim is correct. Saturn's average density is lower than liquid water. Mass divided by volume gives a number below 1, and that number is real. What the meme gets wrong is not the calculation. What it gets wrong is the story we build from the calculation. The first mistake is treating an average as a description of structure. Average density does not tell you how mass is arranged. It cannot tell you whether a planet is layered, mixed, or concentrated toward the center. It cannot tell you how pressure changes with depth. It is one number standing in for a continuous interior. The second mistake is importing Earth-based intuition about materials. On Earth, low density often feels like weakness. Light objects bend or break more easily, and empty objects feel flimsy. That association is emotional, not physical, and it fails for planets. A planet is held together by gravity, not by stiffness. Gravity does not care whether the ingredients feel light in your hand. As long as there is mass, gravity pulls inward and pressure builds. In Saturn, pressure climbs so high that hydrogen becomes a dense fluid, and deeper layers become electrically conductive. None of that is suggested by the word float. The third mistake is imagining a planet as a passive object inside a container. Floating is a relationship between an object and a surrounding fluid that supports it. Saturn is not an object in a tank. Saturn is the dominant mass in its neighborhood. If you place Saturn near a vast body of water, Saturn would reshape the water through tides and gravity, rather than rest gently on a surface. The familiar picture fails at planetary scale. The fourth mistake is confusing composition with behavior. Saturn is made mostly of hydrogen and helium. Those elements are gases in many everyday conditions, but inside Saturn, they do not behave like thin gas. They behave like a deep, compressed medium, whose properties change with pressure. Calling Saturn a gas world can be chemically correct and physically misleading at the same time. The meme also hides a deeper lesson about size. Saturn looks large and smooth, so the mind expects emptiness. But size in giant planets is not a measure of hollowness. Size is an equilibrium between gravity compressing inward and pressure pushing outward, with heat helping maintain that pressure. Saturn is large because light elements can remain expanded under heat, and because its gravity compresses them less than Jupiter's does. Puffy is a balance point, not a sign of weakness. This is why the meme is true but dangerous. It gives a correct number, then invites an incorrect mental model. A correct number can still be used in the wrong way, the way a good map can still be read backwards. The map is not lying, it is just missing the terrain that gives it meaning. The danger is subtle because the meme feels finished. It sounds like a conclusion when it's really only a starting point. Once the brain accepts the image of a floating planet, it stops asking the next questions and the interior disappears. So why does the meme persist? It offers surprise without demanding mechanism. It gives the brain a quick reward, a strange claim about a familiar object, and then it stops. It also feels safe because it seems to be only a number, not a theory. But the misunderstanding enters when the number is treated as a complete explanation. A better way to keep the meme without letting it mislead is to treat it as a doorway. The doorway leads to 3 questions that are more useful than the floating image. What is the planet made of? How strongly is that material compressed by gravity? How does heat move through the interior over time? Those questions replace mood with mechanism. They also scale beyond Saturn. They apply to Jupiter and to many exoplanets whose sizes and densities look strange at first glance. The universe often violates Earth intuition not because it is mysterious, but because the conditions are different. Saturn is a good example because it is visually gentle. Its rings and pale colour invite softness. The meme fits the look, and the look fits the meme. But the physics underneath is not soft. It is a deep gradient of pressure and temperature with layers of fluid matter responding to gravity. If you want one final correction to carry forward, let it be simple. Floating is a comparison about an average. It is not a description of what Saturn is. Saturn is not defined by buoyancy. Saturn is defined by compression. Once that correction is made, the planet becomes more interesting, not less. The rings become part of a gravity-dominated system. The atmosphere becomes the visible edge of a deep interior. And the floating fact becomes a reminder to ask what the number leaves out. That is the real value of the meme. It is a small prompt to slow down and replace a clever image with a physical story. With that story in place, the closing is simple. The same fact returns, but the meaning has changed. One way to feel the difference is to imagine 2 objects with the same average density. One can be a solid block, another can be a shell with dense material at the bottom and light material above. The number can match, while the interiors are nothing alike. Planets are like that, but on a much larger scale, with pressure changing the texture of the same elements. Saturn's average density is a headline, the interior is the article. When the headline is taken as the whole piece, the planet is misunderstood in a quiet, precise way. At the beginning of this journey, Saturn seemed light, a pale planet with thin rings, calm and balanced against the dark. The idea that such a world might float felt harmless, even charming. Now that image can return, but it no longer stands alone. The floating statement was never truly about water. It was about a number, an average density detached from the forces that give that number meaning. Once those forces are restored, the picture changes. Saturn is not light in any physical sense. It carries immense mass bound by gravity that presses inward at every depth. Its softness is visual, not structural. Its calm appearance hides a world shaped by compression. Density remains a useful quantity. It helps compare planets and spot patterns across the solar system. But density is not a verdict. It is a starting point, a signal that something deeper is worth examining. When gravity is allowed back into the story, Saturn becomes coherent. Light elements do not imply weakness. Gas does not imply emptiness. Large size does not imply fragility. Instead, Saturn becomes a lesson in scale. The same rules apply as everywhere else. Mass attracts mass. Pressure builds with depth. Matter responds to its environment. What changes is not the physics, but the conditions. Pressure rises far beyond everyday experience. Temperature reshapes behavior. Simple elements take on unfamiliar roles. Seen this way, Saturn is no longer a joke fact or a trick comparison. It is a system layered and continuous shaped by gravity over billions of years. The rings are not decorations. They are part of that system. The clouds are not a surface. They are the visible edge of a deep interior. The floating line can still be repeated, but now it carries a different weight. It no longer suggests weakness. It no longer replaces explanation. It becomes a reminder of how easily intuition can slip when scale changes. Saturn does not challenge physics. It challenges shortcuts. The planet feels familiar because it follows the same laws as everything else. It feels strange because those laws are operating far from our everyday reference points. That combination is what makes it worth slowing down for. Space is not misleading. Our first impressions often are. When we trade clever images for mechanisms, understanding becomes quieter and more precise. Saturn does not need exaggeration to be interesting. Its real structure is already enough. And that is where this story settles. Not with a surprise, but with clarity. The same fact understood differently in a planet that feels less magical yet more real.